Okay, on to question 7. So question 7, unfortunately, on my page is split a bit weird, but it says, figure 1 shows the horizontal forces acting on a man swimming in the sea, and this is the picture that we need. So we need to describe the movement of the man when the resultant horizontal force is 0. So, quick recap on resultant forces. So if I just draw a free body diagram, so I've got a square there, and what I'm going to do is, let's say I've got a force going in this direction, let's call that 10 newtons. That's got a forward force because there's no backwards force acting on it. In this case, it says that the force is 0 newtons. So for that to happen, there must be a backwards force, also of 10 newtons, and then we would do 10 minus 10 equals 0 newtons. So what it says is there is a resultant force of 0 newtons. So that means the force is the balance. So anything where there is a balanced resultant force, we will or 0 resultant force, we will have a constant speed. So this object is already moving, this person, so we know that their speed is just going to become constant. The man increases force A. Explain what happens to force B and to the movement of the man. And it's worth 4 marks. So, it's going to require a bit of a longer answer, this one. And it is also an explain question. So we have to say why. So the first thing, force A increases. So let's have a look. So again, we'll think about our free body diagram. So I'm going to draw this one up here in this top corner there. So if force A is that force there. Now at the moment, they are the same, they are balanced. Let's just say 10 newtons and 10 newtons. But if that changes, so this force A becomes bigger, let's make it 15. So that's a slightly larger force, 15 newtons. You can see that now the resultant force is no longer balanced. No longer will it travel at a constant speed. We'll have 15 minus 10, so we'll have 5 newtons acting in that direction. So that will cause the man, in this case the swimmer, to speed up. So the first thing that we'll say is explain what happens to force B and the movement. So the swimmer will accelerate. Okay, that means that we'll get faster. The swimmer will accelerate, and then what will happen? Okay, so what will happen? So they'll start to get faster, but as they get faster, the force B will start to change because the swimmer is going to start hitting more and more water. The faster they go, the more water particles the swimmer hits per second. So what will happen is that force B, the backwards force, if we look at my diagram over here, will also start to increase. The faster they go, the more water particles it hits, the more water resistance there will be, until the backwards force and the forward force are equal again. And in that case, we'll end up with 15 minus 15, which goes back to 0 newtons, and we'll end up with a top speed again, okay, a constant velocity. So let's add that into our answer. The swimmer will accelerate. This will cause force B to increase as he will collide with more water particles each second. Force B will increase until it is equal to force A, 0 newtons, until it is equal to force B. At that point, the swimmer will travel at a new constant speed, and it will be faster than the one shown in the diagram, and the diagram is called figure 1, faster than shown in figure 1. Okay, so we always read our answer back and just check we've done what we said. So we were trying to explain what happens to the force B and the movement. So the swimmer will accelerate. This will cause, so we've explained a little bit about the movement. That should get us 1 mark. Swimmer will accelerate. This will cause force B to increase. So we've talked about what will happen to force B. Have we said why? This is because he will collide with more particles each second. So that is why. So therefore force B will increase until it's equal to force A. And at that point, the swimmer will have a new constant speed, again talking about the movement, and this movement, this new constant speed is faster than the previous one, the one that is shown in the diagram, which is called in figure 1. Yeah, I think that very much should get us all 4 marks there. Okay, part C. Now, part C is one that's going to require us to draw a resultant force diagram. Now, in order to draw a resultant force diagram, you're going to need a few things. You're going to need a ruler, you're going to need a pencil, and you're not going to need an iPad. Yeah, so I'm going to struggle to do this one on my iPad because I don't have a ruler and a protractor. I need a protractor as well. So what I'm going to do is I'm going to swap over to a piece of paper and try and do some clever editing where I seamlessly jump to the paper and can carry on the video from there. Okay, so we have now jumped to my visualizer. I've left the question on the screen, so you should be able to see my iPad for the minute. The reason I wanted to leave this on is because when we get these type of questions, often we get this grid on the exam paper, and it should be in centimetres. My advice is to not use this grid. My advice is to use a ruler and to use a scale diagram drawn in centimetres, because you will need to measure the resultant force, and that will be very difficult to do using these centimetre squares. So let's see. There we go. Right, so I've just written this out. I'm going to zoom out a little bit just so we can see a little bit more clearly. So this is the same question. So we've got a boat moves through the sea. There is a force of 3,000 newtons to the west of the boat, and there is a force of 1,000 newtons to the south of the boat. All right, now I'm going to do what I do on a normal. Sorry about the noise, but I'm just grabbing the highlighter. So 3,000 newtons, smudgy, and 1,000 newtons. And the key thing is that you've got to use the directions. So we're told that we've got the 3,000 to the west and the 1,000 to the south. So whenever you're going to draw a resultant force diagram, I would always recommend you do a sketch diagram first. So I'm just going to do this in this top corner here. So the 3,000 is to the west. So we've got an origin point, and we've got our 3,000 going to the west, like that. All right, and then we've got a 1,000 going to the south. So we've got 1,000 to the south. So our diagram is going to look like that. The reason I recommend we do that is because quite often people normally draw like the standard one of these would be like that shape, and people draw that and they just think they see those forces and they draw that. So you've got to use those directions. So what we now need to do is we need to come up with a scale that we're going to use, because we're going to draw this in centimeters. So what I would do is get your ruler, and we want to draw the biggest one we can possible. Now I'm going to move my page up a little bit, try and keep those 3,000 in view. Now I can't use 30 centimeters. That would be the ideal scale. If I just use 30 centimeters, and I could see each centimeter is equal to 100 newtons. I could have done that, but I can't fit that in. But I can do half of that. I can do 15. All right, and this is just a piece of A4, so you should be able to do that in your exam as well. So that would be the scale I would have recommended using in the exam. So that's what we're going to use. So we're going to use 15 centimeters. So I'm going to draw a 15 centimeter line. Being really careful, because this is a scale diagram. Any inaccuracy in our drawing will result in an inaccuracy at the end. So we have to be as careful as possible. This point here was our origin point, so that's where it started from. Let's put a little mark there. And this part here is our arrow. Now, key thing is your arrowhead you must have an arrowhead to show which way the force is going. but it can't be stuck on the end of that 15, because otherwise that will lead to an inaccuracy. So you should end up with something like that, and then we can just complete that and put that other arrowhead on. So that is our first line. So we've got a 30 centimeters, and that is representing a force of 3,000 newtons. So we can use that to work out our scale. So if I just grab my calculator, so we've got turn it on, 3,000 newtons, and we've put that into 30 centimeters. So no, we have not. We have absolutely not. I've lied to you. 3,000, and we put it into 15 centimeters, didn't we? So each centimeter is worth 200 newtons. So I need to change that. That's actually 15 centimeters. So we can just write a scale here. So 1 centimeter is equal to 200 newtons, and we'll need that for our answer at the end. Right. Luckily I did this in pencil, so I could have just rubbed that out. So what does that mean to my number down? So I've got 1,000 newtons that I have to draw down. So how large does that need to be? So I'll just use that scale. So each one is 200. So after I've got 1,000 divided by the 200, so I need 5 centimeters down. So let's do a 5 centimeter line going down, and you need to make sure again that this is perfectly at a right angle. So what you might want to do is get your protractor and put on that 90, so you know this is a perfect right angle, your line. So I think I said 5 centimeters. I did, just check that. So 5 centimeters, you can see I'm lining up. Now that just goes just beyond this line, and it's got to be really, really accurate. And that's what I mean about if you use the squares in the exam, sometimes you can end up drawing it to the squares rather than what it actually needs to be. So that's what I've got. So this is the first part of drawing a scale diagram. Then, so we've got our origin point here, which is where the boat is, and then the boat is being a 3,000 newton force in that direction and a 1,000 newton force. What we have to do is we have to figure out the magnitude. So magnitude is size. So we want the magnitude. I'm just going to box that. And we want the direction. So those two things are going to give us our marks here. And we also have to draw this vector diagram. And the vector diagram just means vector is something that has a magnitude and a direction. So one of these basically, an arrow diagram. And it has to be to scale. So what we do now is we create a parallelogram. Now luckily this is dead easy to do. You just create parallel lines from what we've drawn here. So again, I'm just going to get my protractor, put it on that line, and I want a 90-degree line down, and we should use a dashed line for this. Alright, and just keep drawing that line down, and then we do the same for that arrow, again keeping that at 90. Okay, 90 degrees from there. I'm just making sure it's pretty much exactly parallel and nice and straight, so that should be to scale as well. Apparently I can't do a dashed line as quickly in the horizontal as I can in the vertical. There we go. So we now create our parallelogram, and basically we need to draw our line. So the effect of this force, the resultant force, is going to come from the origin to where these lines intersect. So we're going to draw that. So we put our pencil right on the origin point and line it up perfectly with our intersection, and we draw our line like that, and then we put our arrowhead on here to represent which way that's going to go. So you'll get a mark for making sure you've done this diagram. So that is the result. The boat will move in this direction. As you can see, it's a force that's slightly bigger than that and a lot bigger than that. So we're going to have a force that's somewhat a little bit bigger than 3,000 newtons. The way we figure out the magnitude is we measure it in centimeters, and then we use our conversions. So we have got 15 point, that's the 15.5, so 15.6 7, 8. 15.8. So it's 15.8 centimetres. So what we want to do in order to convert that back into newtons is just times it by our conversion factor here. So every centimetre is 200, so we just do 15.8 times by 200, and this gives me 3160 newtons. So the magnitude of my force is 3160, but I also need the direction. And the direction, basically we just need to find the angle here from the horizontal, or you could give them the angle here from the vertical, as long as you mention in your answer which one you are doing. I'm going to do this one here, so I'm going to look at the angle from the vertical, from the horizontal. So you just place your protractor on, like that, make sure we've got a nice straight line, and you can see that this is less than the 20, much bigger than the 10, that is about 18 degrees. Okay, so my answer, where you would write this on your paper, you would write something like this. So we have got a force of 3160 newtons at 18 degrees, just move that up a little bit, to the horizontal. So if you go in the vertical, you would have just measured that one instead, and instead at however many degrees to the vertical. Okay, back to the iPad for the next part of the question. Okay, back to the iPad. So you can see I've just done a sketch of what we did on the paper. This one here isn't accurate, but I've just copied the same numbers down that we managed to get. The reason I put it on here is because we need it for the next part. So part D says the force to the south of the boat increases. What effect does this have on the resultant force of the boat? So if it's the force to the south, that's the downward force. So let's see what that would look like. Let's use a different colour. So if that force increased to something like that, so let's say it went up to 1500 newtons, well, what would happen was that this would increase that way, and this would increase here. So our resultant force would actually be like that. So we could see two things have happened. It's slightly larger, so the size of the force increased, or the magnitude, and also the direction's changed. It's now acting more towards the south. So they're the two things that we're going to mention. So we're going to say the size, which is magnitude, of the resultant force increases, and the direction of the force is now more towards the south. You could say, it was 18 degrees before, wasn't it? So we could say, the horizontal force was previously 18. It would now be a larger number than 18. But that's what we're trying to say, is that it changes towards the south. Okay, that's the end of that question, and join me back for question 8.